Okay, so our class this morning will be focused on module 7. And as you can see, we're nearing the end of the course. So just one more module to go. And the topic of module 7 is linear momentum. So intuitively, when you hear the word, momentum, it suggests it invokes the notion of a fast moving object or a very massive object. So the word momentum is used every day in different contexts. For instance, it's common to hear of a team, as a sports team having momentum. It's common to hear people refer to a candidate in an election, having momentum. The idea that links all these different usages is the idea of things moving in a given direction. In the diagram displayed on the screen, you have a trailer on one side and a small car on the other side. Intuitively, one would say the trailer has more momentum because it's more massive compared to the car. So this is entirely consistent with the scientific definition of momentum. Now, so momentum is defined simply as the product of an object's mass, m, and its velocity, v. So object's mass, that's the missing word, and the velocity v, and it's denoted by the symbol p. So momentum has both magnitude and direction, and it's thus a vector quantity. The direction of momentum is the same as the direction of the velocity of the object. So P equals m times v. Since mass is a scalar quantity, so it's just a number, when you multiply a vector by a number, by a regular number, you obtain a different vector. So multiplying v by a scalar m gives you a new vector called p, which is known as the momentum. So, momentum is essentially the amount of motion in an object, and it depends on the mass and the velocity. The SI unit of momentum is kilogram times meters per second. And this is consistent with the formula. So P equals m times v. M is mass. Mass is measured in kilograms. V is velocity. It's measured in meters per second. So the unit for momentum is thus kilogram times meters per second. Now, more about linear momentum. Since momentum is a vector quantity in 2 dimensions, momentum has the following x and y components. So P sub x will be m times v sub x, and P sub y will be M times V sub y. And we know that for any quantity A with direction theta, A sub x is A cosine of theta, A sub y equals A sine of theta. So you could thus say that P sub x is equal to M V sub x, which is V cosine of theta, and P sub y is equal to M V of y, which is V sine of theta. So given the velocity and its direction, you can find the x and y components of the linear momentum. So this applies to two-dimensional motion. Now, if an object is moving in one dimension, you don't really need x and y. You would just say P equals M times V, with the understanding that V is in one dimension. So momentum is also related to the kinetic energy of a system or particle, and the relationship is shown here. So Ke equals P squared divided by 2M. And it's easy to show that this is a valid equation because P is M times V. So M times V, if you square this and divide by 2M, you get M squared, V squared divided by 2M. One of the M's will cancel. And then you're left with mv squared over 2, or just 1/2 mv squared, which is the equation for kinetic energy, translational kinetic energy. So what this relationship says is that if we know the linear momentum P and the mass of a particle, we can calculate the kinetic energy. Conversely, if we knew the kinetic energy, we could find the momentum. So if we transform this equation, you have P squared equals 2M times Ke, which means P equals square root of 2M times the kinetic energy. I'm putting the parentheses to emphasize that Ke is just a notation of kinetic energy. It's not two different variables. It's not K times E, it's just the kinetic energy. So if you know the kinetic energy of a particle, you can compute the linear momentum. Okay, so let's talk about the next quantity, which is impulse. So impulse is simply the change in momentum. So the change in, you could simply write impulse equals change in momentum. So delta P the symbol for impulse is I. So I equals delta P. Okay, and since we know that P equals M times V, so the impulse is simply equal to the change in M times V. But since the mass of regular objects is constant, so you can pull the M out and you can write this as M times change in V. Now this will be different for objects with changing mass, like a rocket. You know, when a rocket is launched, it's loaded with fuel, and part of the fuel burns up in propelling the rocket. So as the fuel burns up, the mass of the rocket changes. And at different stages, different parts of the rocket will be discarded. So in such an analysis, you wouldn't consider the mass as constant, but for all other everyday objects, the mass is, considered constant. That's why the rocket propulsion problem is treated differently towards the end of the chapter. So this is the impulse for an object M undergoing a change in velocity V. And here you could further write this as M into V for final minus V initial. Change in V or change in any quantity is simply the final variable minus the initial variable. Okay, so in the next step we're going to do is to connect Newton's second law to momentum. So just remember from the previous slide, we said the impulse, which is equal to the change in P, is equal to M times change in V. So what this means is that if we divided both sides by time, we would get M delta V divided by delta T. So this simply means that the change in P divided by change in T, if you recognize this, if you look carefully, you recognize that change in V divided by change in T is the acceleration. So that means change in P divided by change in T is M times A. And M times A, we recall, Newton's third law, sorry, Newton's second law, F net equals MA. So one could say that the net force is equal to change in P divided by change in T. Okay, and from here, we could take it further and say that this relationship means that change in P is equal to F net times delta t. You can put the arrow on top to emphasize the fact that P and F are vectors. So what we've derived is that the average force or the net force during the interaction between different bodies is equal to the change in momentum divided by time, or the change in momentum, which is the impulse, is simply the average force divided, multiplied by time. So this is another important relationship. Okay, so if you're asked to compute the average force or the net force, as long as you know the impulse or the change in momentum, you could divide the change in momentum by t to get the net force. Conversely, you could multiply the average force by time to get the impulse. Now, why is momentum important? Or why are we studying yet another new quantity? Remember, from the beginning of this course, the simple goal for physics 1 or classical mechanics is to study the motion of objects. To study the motion of objects, you need to know their position, you need to know their time, you need to know the rate at which their position is changing, or the velocity. You need to know the acceleration if the object is speeding up. So that's the fundamental goal of physics 1, to study the motion of objects. And the first approach is, if the acceleration is constant, then you could do all of this, you could achieve all of this using the equations of motion in module 2. And if the motion is linear, that is in one direction, then you just need the equations in one dimension. Now, if the motion is two-dimensional, then you need to know the concepts of vectors, X and Y components, and you need to know the concepts of projectile motion. If the object is projected into the air and is moving only under the influence of gravity. Now, in module 4, we learned another approach. If we couldn't use the equations of motion, we could use the concept of forces, the concept of equilibrium, Newton's laws. By drawing free body diagrams, we can apply Newton's second law and solve the motion of an object. Then in chapter 5, we consider the case where the object was moving in a circle. That's rotational motion. And we derive similar equations that could be used to study the motion of such an object. And then in chapter 6, if the equations of motion didn't work, or if the acceleration was not constant, we learned that we could use energy considerations. We could use the law of conservation of energy to solve the motion of objects. We could use the fact that if only conservative forces are present, then the energy must be constant. If non-conservative forces are present, then the difference between the final energy and the initial energy will be equal to the work done by non-conservative forces. So now in chapter 7, we're introducing a new concept called momentum, because in some cases, it's not possible to use equations of motion. We may not even know the forces, so we cannot use Newton's second law. We may not know the acceleration, yet the tool that we will be left with in this case will be the concept of momentum. And because this quantity is known to be conserved, it offers us another tool, you know, to solve the motion of different particles. So during, and this is important, especially during collisions, when two things collide, it may be difficult to determine the acceleration. The forces may not even be constant. The force acting, let's say think of two cars crashing. The force during the crash is not constant. It varies over time. So you couldn't apply Newton's law. You couldn't use the equations of motion. But the fact that we know that the momentum of the two cars must be conserved if the system is isolated. So that gives us another tool in our toolbox for physics 1. So we've defined momentum, we've defined the change in momentum, which is impulse. We've connected the change in momentum to the average force. Now let's look at some everyday life implications of this concept of momentum and impulse. So in everyday life, I'm sure everyone in this class, you know, is a driver. And in every state, I'm sure there is a mandate for seat belts when driving. It's a felony, you know, to drive without a seat belt. Now, one may see this just as government intrusion in trying to tell people how to do things, but a deeper observation will show that this is rooted, or this is based on physics, and this is actually for your safety. And let's look at it in terms of this equation. The average force on an object during collision is equal to the change in momentum, or the impulse, divided by the collision time. Now, as you can see in this equation, during any collision, the change in momentum of the two objects is always the same. So what makes the difference between the force that each of the objects in the crash experiences is the collision time. So in this equation, because the collision time is in the denominator, change in momentum or impulse. Because the collision time is in the denominator, the longer the collision time, the smaller the average force, or the net force. And the shorter the collision time, the larger the average force. Remember, the change in momentum is constant. So if T is bigger, you're going to end up with a smaller F, because when you divide a fixed number by a larger denominator, you get a smaller answer. So basically, let's put it this way. Let's say you have $100 to divide to different students. So if you divide this $100 to just 2 students, then each student goes away with $50. But if you divide the $100 to 100 students, then every student goes away with just $1. So as you can see, in this case, the number of students will be the denominator, and then the top will be the fixed amount, the fixed dollar amount, which is $100. So in a collision between two objects, whatever will make this collision time longer will reduce the amount of force that the different objects experience. So in the case of a car, this car is going, let's say, 70 miles per hour on the highway. As we learned from Newton's law, this driver is also moving forward at 70 miles per hour, and any other passenger in the car. So in the event of a collision, the seat belt, which is also known as a passenger or a restraint system, the seat belt restrains the driver from crashing into, let's say, the steering or any solid part of the car in front of him or her. So when the car stops abruptly, according to Newton's first law, the passenger has the tendency to keep moving forward at the same speed, 70 miles per hour. If there was no seat belt, then the driver could actually be ejected from the car. The driver could actually crash through the windshield and be projected out of the car at the speed 70 miles per hour. But the seatbelt holds the driver back, thereby increasing the time it takes, or slowing down, essentially slowing down the forward motion and increasing the time it takes for the driver to have impact with the steering or any hard part of the car. And by increasing the collision time, the net force experienced by the driver from the steering or any hard part of the car is greatly reduced, improving their chances of surviving in a car crash. That's why you mandated to wear seatbelts, but it's actually for your security, because of for your safety. The same thing applies to restraint systems like airbags. So airbags are devices like inflatables that will pop up during a crash. The same concept applies. The purpose of the airbags, again, is to provide a cushion between the driver or the passenger and the surrounding hardware, or the iron or the different solid parts of the car. So by providing that cushion, the airbags reduce or increase the collision time. This also factors into the various design of cars today. Most cars are designed, with the windshield further away from the passenger or the driver, so that in case of a crash, the driver doesn't have an immediate collision with the windshield. So this simple equation, has many everyday life application. You can apply this also in contact sports like football, rugby, where different players, tackle each other. So let's look at, before we move forward beyond impulse, let's look at a couple of examples. So calculate the momentum of a 110 kilogram football player running at 8 meters per second. So the mass, 110 kilogram, V equals 8 meters per second. The momentum would be equal to M times V. So 110 kilogram, 8 meters per second. And this will give you 880 kilogram meters per second. Okay. So this is examples number 7.2.1. If you have a copy of your textbook open, Seven point 2.1. Now, as Pat B said, compare the particles, compare the player's momentum with the momentum of a hard thrown 0.410 kilogram football that has a speed of 25 meters per second. So momentum for the football So the second part says, compare the player's momentum to that of a 0.410 kilogram ball thrown at 25 meters per second. So you can calculate the momentum of the ball, mass of the ball, times the speed of the ball, which is 0.410 kilograms multiplied by 25. And this is 10 kilogram meters per second, 10.3. So if you compare the momentum of the player to that of the ball, you have 880 kilogram meters per second divided by 10.3 kilogram meters per second, and this gives you 85. So that means the momentum of the player is 85 times that of the ball. So even though the player is only running at 8 meters per second, because they're more massive than the ball, the player has more momentum than the ball. Example number 7.2. Says during the 2007 French Open, Venus Williams hit the fastest recorded serve in a Premier women's match, reaching a speed of 58 meters per second. That's roughly 209 kilometers per hour. What is the average force exerted on the 0.057 kilogram tennis ball by Venus Williams racket, assuming the ball speed just after impact is 58 meters per second, and that the initial component, horizontal component of the velocity before impact is negligible. And that the ball remained in contact with the racket for 5 milliseconds. Okay, so here we want to find the average force. We know that the speed of the ball is 58 meters per second. And so the ball started from rest, but after being hit, it acquired the speed of 58 meters per second. So the initial velocity is 0. And we know that the collision time between the racket and the ball is 5 milliseconds. That's 5 times 10 to the minus 3 seconds. Milli means 10 to the minus 3. And the question says, find the average force or find the net force. So based on what we just studied in the previous section, the net force is equal to the change in momentum or the impulse divided by the time. And change in P is simply M times delta V over delta T. Okay, so this is M V minus V initial divided by delta T. And so the net force is equal to the mass of the ball is 0.057 kilograms. So the net force equals 0.057 kilograms into 58 minus 0 meters per second. Divided by 5 milliseconds, 5 times 10 to the minus 3 seconds. So this means that Venus Williams exerted a force of 661 newtons to achieve the record speed of 58 meters per second or 209 kilometers per hour. So this is how you would apply the concept of net force or average force with momentum. Now take note this problem could simply have asked you to find the impulse. And the impulse will just be the change in P, which is M times change in V. So 0.057 kilograms times 58 minus 0. That would be the impulse. Okay. And the impulse would be 3.3 kilogram meters per second. Now, it's important to also note that during collisions, the force, the actual force is not constant. So it changes over time. So if you look in the textbook, there's a sketch that shows, suppose this is the force, and this is the time. The force, the variation of the force may actually look like this. So the area under this graph, which is the product of F and T, remember when you multiply two sides of a rectangle, you get the area. And if one side is the force and the other side is T, so F times delta T is impulse. That's what we just derived in the previous section. So when the force is not constant, or when the force varies with time, you could compute the force, the impulse by computing the area under the graph. Now, if we calculated the average force, so the average force, this is like the maximum force, and the minimum is 0. So the graph starts at 0, peaks at this point. So the average will be somewhere here. So if we computed the area, this area, you notice that this area is roughly equal to the area of the space under the red curve, okay? If you take this part and this and add this part together, those two parts will almost approximate to the space above. So, but if this is your T final, this is your T initial, then the area of the shaded rectangle is this area is equal to F average times delta T, which again is your impulse. So when presented with a graph and ask you to find the impulse, all you have to do is compute the area under the graph, or under the F versus T curve. Now let's talk about conservation of momentum. So simply put, when two objects collide, the momentum after collision is equal to the momentum before collision. This is a straightforward extension of Newton's third law. Newton's third law says action and reaction forces occur in pairs. So when two objects collide, assuming there's no third force, there's no external force interfering with the collision, the change in momentum of the two objects must be the same. So, and that's because the net force, so let me write this. So F12 is equal to F2 minus F21. Okay, that's Newton's third law. Or you could simply say, if you're looking just at if you're looking just at the magnitude, then you would say magnitude of F12 equals magnitude of F21. But remember, from the previous expression we just derived, the net force is equal to the change in momentum divided by time. So delta P for the first object divided by delta T is equal to minus delta P for the second object divided by delta T, because the two objects are in contact for the same amount of time. So delta T is the same. So you could cancel delta T on both sides, multiply both sides by delta T, that will go away. And you end up with delta P1 plus delta P2 equal to 0, which is the statement of conservation of momentum. In other words, you're saying that P1 plus P2 is equal to a constant. Now, if we write this out explicitly, the change in P1 would be M1 times the change in V1. So M1 V1 final minus V1 initial. The change in P2 would be M2 times V2 final minus V2 initial. Remember, you have two objects. This is M1, and then this is M2. So the object M1 has an initial velocity called V1 initial. This time we have to differentiate the two objects by the subscripts 1 and 2. 1 stands for the first object, 2 stands for the second object. I stands for initial. So this is before the collision. Now after the collision, let's say M1 bounces back. So you have M1 now going this way. This is your V1 final. And then suppose M2 keeps going to the right. So this will be a V2 final. And this is your M2. So it's important to keep this in mind. This is the picture that we're working from. So if we expand the parentheses here, you get M1 V1 final minus M1 V1 initial equals, plus M2 V2 final minus M2 V2 initial equal to 0. So if we rearrange this, move the negative terms to the right, the negative signs will become positive. So we move minus M2 V2I to the right-hand side and minus M1 V1 initial to the right-hand side. We'll be left with 2 positive terms on the left, 2 positive terms on the right. So M1 V1 final plus M2 V2 final equal to M1 V1 initial plus M2 V2 initial. So this is the most general equation for the conservation of linear momentum. So what you're simply saying this is that the sum of momentum before the collision, P initial equals P final. Before the collision, this is the momentum of mass number 1. This is the momentum of mass number 2. So you add those two, you have the initial momentum. After the collision, this is the momentum of mass number 1 and that of mass number 2. So the sum gives you the final momentum. So this is your starting point for all problems involving the collision between 2 objects. Now, if one of the objects was at rest, that means its velocity will be 0. So you would cross out that term, and this will greatly simplify the problem. So this is how you state conservation of momentum. P final equals P initial, or the explicit expression is the one in the box. Now, there are 2 types of collisions. So collisions are broadly classified into 2 types. There is elastic and elastic collisions are collisions during which kinetic energy is conserved. So that means in addition to M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. One could also say 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared equals 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. Okay, so these 2 equations will be valid for elastic collisions. Now, if a collision is not elastic, as long as the system is isolated, the law of conservation of momentum will always hold. So the first equation will always be true, regardless of whether the collision is elastic or not. But the second equation only applies when you hear the word elastic. That means in addition to conservation of momentum, you can apply the conservation of kinetic energy. So the second type of collision is inelastic. So as you will guess, these are collisions during which kinetic energy is not conserved. Again, take note of the word, the phrasing. The phrasing says kinetic energy is not conserved. It doesn't say energy is not conserved, because energy is always conserved, okay? If the energy changes, it means some has been converted to another form. You cannot create or destroy energy. But during inelastic collisions, the kinetic energy before collision will be different from the kinetic energy after collision. So when that happens, you characterize that as inelastic. But still, during inelastic collisions, the momentum is conserved. So P initial equals P final. I'm just going to write the short form. You can write out the expanded form. But you cannot say that KE initial equal to KE final. That is not true. Okay, so the final kinetic energy is not equal to initial kinetic energy. So when you're solving problems for inelastic collisions, you need to remember this. Now, there's a subset of inelastic collisions known as perfectly inelastic collisions. Perfectly inelastic collisions are those during which the two colliding objects stick together to become one object after the collision. So these are collisions during which the two objects stick together to form one object. And we have multiple examples in everyday life. So basically you have object number one, you have object number two, and then after the collision, you have object number one and object number two. Become one object. And then the two objects have one common final velocity. Now, a simple example would be in a football game, the defensive player tackling the running back and wrestling them to the ground. So before the collision, the running back is running in one direction with the ball, the defensive back is running in probably the opposite direction, chasing the running back. And when the defensive player tackles and holds onto the running back or the quarterback and gives them a sack, that corresponds to M1 and M2 becoming one object. Because at the instant when the defensive player tackles the player with the ball and holds onto them, that becomes, like two objects becoming one. You could also have the case of a bullet being fired into a log of wood and the bullet, remaining in the wood. So that's also an inelastic, a perfectly inelastic collision. So the bullet and the wood are separate before the collision. After the collision, the bullet and the wood become one object. Another example would be throwing a lump of clay on an object. So if the clay sticks on the second object, it becomes a perfectly inelastic collision. So the law of conservation of momentum in this case, for perfectly inelastic collisions, you just have M1 V1 initial plus M2 V2 initial equals M1 plus M2 V final. So the law of conservation of momentum is simpler for perfectly inelastic collisions. The final velocity in this case will just be M1 V1 initial plus M2 V2 initial divided by M1 plus M2. Okay. So that's perfectly inelastic collisions. And as I illustrated in the previous sections, there are several examples in the book. There's example number 7.5.1 for elastic collisions. So there's an example 7.6.1 for inelastic collisions. Go through those examples, follow the steps, and see if you understand the solution. If you have any questions, you can reach out to me. So let me write it here. So review. Examples. 7.5.1. Seven point 6.1. And then for completeness sake, read the section on two-dimensional collisions and rocket propulsion. So when we meet again next Tuesday, there will be a review session for module 7. And of course, the test is on Thursday. So make sure you've set up your appointment for the test.